Hey students, today we're going to be discussing Earth's energy budget. Now before we get started, let's make sure we're all set up. A few things that you should have. One, you should have already completed the electromagnetic radiation and how it interacts with the Earth's atmosphere, which was the lesson prior to this one. So make sure that you've gone through that first. If you haven't done that yet, it will be harder to understand this lesson. So the other thing is you should go ahead and open the notes sheet, or if you'd like to print it, on the note sheet that your teacher has provided, because you're going to be taking notes as we go, just as you would if you were listening to a lecture. And then you're going to submit that note sheet as an assignment to your teacher. So if you haven't already either printed that or opened it digitally to write in, take a second, pause the video, and do that. Okay, next there's a couple resources you can use for this. You can use this this lecture, or you can also use the thing links that are referenced on the assignment sheet. You'll notice for each topic, like part 1 on the worksheet Earth's Energy Budget, there's a bit.ly there, and you can navigate to that bit.ly and learn more by clicking on the little buttons that are on the picture. Now, that has a small amount of information on it, and some people like a little bit more in-depth information. So this will be supplemental to that, and it'll include a bit more detail about what's happening here so you have a better understanding. So with your notes open, I'm going to kind of go in order and make sure that I specifically answer each question, and I will mention the number of those questions as we're going along. So you should see the first diagram I want you to look at is the Earth's energy budget here. Now, if you think about what is a budget, if you're talking about a budget for money, what is that? Well, in a budget, we keep track of how much money is coming in to an account, and we keep track of how much money is going out of an account. And it's important to know that balance so we don't spend too much money or save too much and we're spending what we need to. But the idea here is that we're looking at energy that's coming into the Earth and energy that's leaving the Earth. So let's talk real quick about what kind of radiation, this is question number 1, what kind of radiation is the incoming radiation that's mentioned here? Well, we've talked about radiation, and if we go to this slide here, you may remember that the sun emits all of the spectrum of electromagnetic waves. So quick review, remember our low energy waves are like radio waves and microwaves. Our medium energy waves are our infrared and ultraviolet, which we'll be talking a lot about in this unit. And our high energy rays are X-rays and gamma rays. And the sun is emitting all of these wavelengths and they are hitting the Earth. So going back to this, question number 1, the types of radiation are all of the different types of waves. Radio waves, gamma waves, visible light, all of them. What kind is the type of incoming that is the highest is actually visible. And we'll look at that a little bit later, but for now, for number 2, just go ahead and put visible. And that it kind of makes sense if you look at the organisms that live on Earth. Why are so many organisms adapted to seeing the visible spectrum? Because that's the highest amount of, type of waves that are coming in are visible. So a lot of eyeballs and things like that have evolved. Organisms have evolved to see that visible light since it's so abundant. So let's look at what happens to all of those different kinds of rays, this 100% of incoming energy. What happens to that as it starts to enter the thermosphere and passes all the way down to the Earth? There's 3 things that can happen. First, the light can be reflected by the atmosphere. So you can see it can be reflected directly, it can be reflected by the clouds or from the Earth's surface. So light can be, not just the atmosphere, but it can be reflected as it comes in, that visible light. And look at, if we add that up, this is about 30% of the light that is incoming, all right, is actually reflected. Well, that didn't work very well. It's okay. If we go on to the second thing that can happen to incoming radiation is it can be absorbed by the atmosphere. So 16% is absorbed by the atmosphere and 3% is absorbed by clouds, water vapor in the clouds. So that's roughly 20%. So we've got 30% reflected, 20% is absorbed by the atmosphere. That means only about 50% overall reaches the surface of the Earth. So the third thing that can happen is that this can be absorbed by the land and the ocean. So that's our third thing that can happen to radiation as it enters the atmosphere. So those are the three things that are happening to all of that incoming radiation. Now let's talk a little more specifically about number 4, where it says, how is incoming solar radiation absorbed by the clouds in the atmosphere? This is where our last lesson comes in. If we're focused on this portion right here, the absorbed by the atmosphere, we know from our last lesson that there are a few things that can happen that can absorb radiation as it comes into the atmosphere. So let's look at this slideshow, and you'll notice this is from probably from the last lesson here. Here's the types of absorption that can happen as energy comes into the atmosphere. One thing that can happen is the radiation, especially high energy radiation, can cause atoms or molecules to lose electrons. So that process, if you remember, this process is called ionization. Another thing that can happen is if we have not quite as much energy coming in, an electron can get excited to a higher energy level, and then when it falls back down to a lower energy level, it will give off light. So this is called excitation. Another way that incoming radiation can be absorbed is by photodissociation down here. And so we saw this with oxygen and with O3, which is ozone, how those molecules up in the stratosphere, they absorb high amounts of UV radiation. And when they do, it causes them to break apart. And we looked at that, the exothermic nature of the dissociation of ozone last week. And so this is another type of absorption by the atmosphere that happens. And the last one, of course, is excitation, which is these water molecules doing all kinds of bends and stretches. Now, I want you to keep in mind especially this process of vibrations, because that is one of the ones we're really going to focus on when we start talking about the next graphs and as we look at the greenhouse effect. And notice how these water molecules, there's not just one way they can vibrate, there's multiple ways that they can vibrate, and that's going to be important as we move forward. So those are a few of the ways that incoming radiation can be absorbed by clouds in the atmosphere through ionization, photodissociation, excitation, and vibration. So number 5 says, what type of radiation is the outgoing energy? So think about the 50%, all right, of radiation that actually makes it to the surface of the Earth, and that has a warming effect, right? You've ever gone outside and you stand in the sun and you feel that warmth as those solar rays are touching you. But if you go out and you stand in the middle of the day on a surface, you'll actually feel it's warmer, right? So all of that energy, that's the visible light that's coming in, that's being absorbed by the land and the oceans, is heating up. So that actually then gets transmitted as outgoing infrared. Okay, I'm just going to put infrared. So most of the incoming energy is visible, and most of what's outgoing energy-wise is infrared radiation. And number 6 is accounting for 23% of the outgoing radiation. What carries most of that into the atmosphere? And so almost a quarter of the energy that makes it to the Earth and is absorbed by the ocean and other water is actually carried up into the atmosphere in the form of water vapor. And remember, for number 7, why is that so much energy? Well, it requires a lot of energy to vaporize water because of the hydrogen bonds that form between water molecules. So in order to vaporize it, a lot of energy has to go into that latent heat of vaporization that we talked about in our hydrosphere unit to break those hydrogen bonds to take water from a liquid to a gas. And that's a lot of energy that goes up into the atmosphere. This is also important because that high amount of energy is one way that Earth's temperature is regulated, along with the high specific heat of water, of course. Okay, let's go ahead and look at our next graph here. If you want to navigate to that one with the bit.ly and look at that, you can, but it's up here as well. This graph's a little bit harder to interpret. So let's talk about what's going on here. The first question's asking, how is the majority of solar radiation visible light? How is it showing this? Well, one, it shows it up here, right? So you can see it up here. But also, if we look at the wavelengths down here, the visible spectrum is in this 500 to 700 nanometer range, and that's not exactly right, but it's roughly in that range. When we get longer wavelengths, remember the wavelength is the distance which from the crest of one wave to the crest of another wave, all right, when we're looking at these different types of radiation. If we get higher wavelengths, like here, this is infrared radiation, or shorter wavelengths like here, we're getting into higher energy UV radiation. So because the graph is showing the intensity, and so if you want to think of the solar spectral irradiance as like how much of that type is reaching or is coming to the Earth, it's highest, the intensity is highest in the visible range. The yellow and the red have different meanings here. And so the yellow is, if we look at satellite data, we can see the type of energy that reaches the top of the atmosphere before it actually enters the Earth. And we can see here that that yellow portion is what we see at the top of the atmosphere. The red portion is from detectors on the surface of the Earth, what actually makes it to the surface of the Earth. And so we can see there's a gap here because some things happen to that radiation from as it passes through the atmosphere. You might be wondering what this black body spectrum is, and you don't need to know what that is, but basically that's a theoretical value for the temperature of a certain thing like the sun, and basically theoretically what types of radiation we would expect to be seeing from the temperature of something like the sun. And so it's more of a theoretical value as opposed to a measured value. So we have our two different areas here, and number 3 says, why are those two amounts of energy different? And just like I said, the reason they're different is because what kind of things can happen to that radiation between the top of the atmosphere and the surface of the Earth? Well, it can be reflected and it can be absorbed by the atmosphere. So you'll notice that there's some dips here. Okay, a dip here, a dip here, a dip here. Oops, go away. We're not seeing very much, if any, of the radiation actually reaching the Earth, and especially in our infrared range here. So what's going on with these dips where at the top of the atmosphere we have a certain amount of incoming infrared radiation, but none of that infrared actually makes it to the surface of the Earth? These are the different wavelengths that are absorbed by the different molecules that are indicated here. So as you can see, water absorbs a lot of this wavelength, okay, about, what should we call it, about 950 nanometers. Water also absorbs a lot of this, which is maybe in the 1150 nanometers wavelength. Water also absorbs a lot of this wavelength, and this wavelength, and this wavelength. So water has multiple absorption bands. And going back to all of the different stretches and bends and vibrations that water can do, there are lots of different ways that those incoming rays, those infrared rays, can cause a water molecule to vibrate. They can cause bending, right? So one of them is they can cause the two bonds between hydrogen to bend back and forth. They can cause stretching, lots of different motions. And so each one of those different wavelengths causes water to make some kind of unique vibration. And since there's lots of things water can do to vibrate, that's why so many different wavelengths are absorbed here. Carbon dioxide just has one on this graph. There are others. You'll notice there's a small peak for O2, but not very much. And over here in the UV range, we have our O3, because we know ozone can absorb in the UV spectrum here. Okay. So this is the purpose of this graph is really just to show you that not all of the energy that hits the top of the atmosphere makes it to the surface. And there are specific types of molecules, which we call greenhouse gases, that absorb a lot of the incoming infrared radiation, okay? And that most of the energy that's coming into our atmosphere or entering our Earth, the majority of it is visible light. Now you'll also notice I don't have anything over here in the higher energy spectrum, which would be our X-rays and gamma rays. And I don't have anything over here in the radio and microwave range. That's because the intensities of those are quite small. And also in the purpose of what we're talking about here, most of what we're really trying to focus on is the middle types of radiation here, the UV, the visible, and the infrared. And again, just to reiterate, most of the incoming radiation is visible and most of the outgoing is infrared. So let's go ahead and move on to the last page. Oops, I apologize, I skipped one here. On this slide it says, what's the type of energy that's absorbed by CO2 and H2O? Well, look at all the dips here for CO2 and H2O, and that's going to be your infrared radiation. Other wavelengths like visible, they don't really interact with water or carbon dioxide or any molecules. Visible light can pass through the atmosphere both directions unobstructed. Okay, let's look at our last slide. So our last graph, this is a measurement of outgoing radiation. So this is for measuring from the bottom of the Earth, that infrared that's leaving, and how much of it actually leaves the atmosphere. So what type of radiation is shown on this graph? This is infrared, or IR, and that's not shown anywhere. So how do we know that? I know that because of the wavelength range that is shown on my graph here. One thing to note, the units are different. This is in micrometers, and back here we were in nanometers. So basically this graph picks up around 1,000 nanometers, right, which is about a micrometer here. And then it goes on to longer wavelengths in the 70,000 nanometers or 70 micrometers. This is just a good point of why it's important to know units and pay attention to things like graphs when they have different units and being able to interpret that. Okay, so this is infrared radiation that's leaving the atmosphere. What do the red and the yellow parts mean? So the red here is let's see here. The yellow here, okay, this area here, is what we would expect from that black body theoretical information, what we would expect the temperature of our planet to emit the different types of radiation. So this is what we would expect to see. It's not a observed number, it's a theoretical number. And the red here is what we actually detect, and this is mainly through like satellite data, what we see from above the atmosphere. Okay, so this is again as infrared leaves the surface of the Earth and exits the Earth's atmosphere, how much actually makes it out. So we can see here, why are the two amounts different? Well, again, if we go back to our energy budget diagram here, okay, what are some things that happen to infrared radiation as it's trying to leave the atmosphere? Some of it gets absorbed by the clouds. That doesn't help. Some of it gets absorbed by the atmosphere. Now this is really key right here. This radiation absorbed by the atmosphere, 15%. That is what we call global warming. So as well, it's connected to global warming, but as outgoing infrared radiation interacts with greenhouse gases like water and carbon dioxide, that causes it to vibrate and re-radiate that infrared in all directions. So some of it that gets re-radiated still goes off back into space, but some of it actually gets retained by the atmosphere and keeps bouncing around and continues to warm up our atmosphere. So the amounts of energy are different because outgoing radiation, I'm answering number 3 here, outgoing radiation that's infrared can be absorbed by the atmosphere as it's leaving. Now, these different bands here where we would expect to see some infrared leaving, but we don't, these bands here are those molecules that are absorbing outgoing infrared radiation. And again, we call those greenhouse gases. With the exception of O3, O3 is not really considered a greenhouse gas, although it does do some absorbing of this infrared as it's trying to leave the atmosphere. So the molecules absorbing energy on this graph are water, H2O, which is a greenhouse gas, carbon dioxide, which is a greenhouse gas, and CH4, which is methane. Those are our 3 greenhouse gases that are our primary causes of warming of our atmosphere that trap outgoing infrared radiation and incoming infrared radiation. Again, ozone is also on there, but it's not considered a greenhouse gas, but it is showing on here some absorption due to other processes. So that's a general overview of our Earth's energy budget. And again, the whole point of this is just for you to understand what happens to that visible light as it comes into the atmosphere and some infrared, and what happens as things are leaving that information. Okay, so if you have any questions, feel free to refer to other resources you've been provided, or you can take a look at the thing links that have been provided as well. Thanks.